Welcome to this presentation on advanced dependency injection and aspect-oriented programming with Micronaut. My name is Graeme Rocher. I am an architect at Oracle Labs, where I lead Oracle's contributions to the Micronaut framework. I am also the creator of Micronaut and another framework called Grails. Do connect with me on social at the links on this slide. So on the agenda for today, we are going to do an introduction to Micronaut, an introduction to GraalVM. I'll talk about Micronaut and dependency injection. I'll talk about Micronaut and aspect-oriented programming. And the main part of this presentation is going to be lots and lots of demos. So Micronaut is essentially a build time framework. What that means is Micronaut hooks into your compiler, and at compilation time computes your dependency injection, your configuration injection, any annotation metadata, AOP proxies, and it does so in a completely reflection, runtime proxy, and dynamic class loader free manner, so that literally your application is statically wired together at runtime. This means that a Micronaut is great for a variety of use cases, including things like microservices and serverless applications, but also message-driven applications with Kafka, RabbitMQ, or even JMS in the recent versions. Command line applications as well is also a great way to use Micronaut, as I'll demonstrate today. You can even use it in mobile contexts on Android. Anything that has a static void main is pretty much a good target for Micronaut. And Java, Kotlin, and the Groovy language are the supported languages as of this time, as Micronaut hooks into each of those as compilers in different manners. With Java, it's based on annotation processes. Micronaut also has really great integration with GraalVM. So GraalVM is a new virtual machine out of Oracle Labs that in JIT mode is able to increase your application throughput by 20 to 30%. And it's also able to do a closed world static analysis of your application to produce a self-contained native binary using the native image tool, which significantly benefits cloud deployments and things like serverless with its super fast startup time and low memory consumption. You can also use multiple languages together with the Truffle language framework in things including Java and Ruby and Python and so on and so forth. So to get started with Micronaut, we have a bunch of really great build plugins. One of them, a build plugin for Gradle, is one for Maven. In this demo, I'm going to be demonstrating the Gradle plugin. And it's a simple matter of declaring the Gradle plugin, which is the io.micronaut.library plugin or the io.micronaut.application plugin, depending whether you're building an application or a library, and declaring the version of Micronaut that you're using. The current latest release at the time of this talk is Micronaut 2.3. and which is what I'm going to be demoing in this demo. So in the context of this demo, we're going to be doing a lot of work with dependency injection and aspect-oriented programming. We're going to look at how you can get set up quickly, how to do some basic dependency injection, how to work with different bean scopes, configuration injection and configuration properties, environments, conditional beans, around device, and bean events. So it's really quite a bit to go through. So what I'm going to do initially is I'm going to create a build.gradle file in terminal. And this is an easy way to get going. You don't need much. You just need a text editor or an IDE. I'm going to use VS Code, and I'm going to create a build.gradle file. And I'm going to open it up in VS Code. And as per the slide, I'm going to add my Micronaut plugin to it. So in the plugins box, I'm going to say ID is io.micronaut.application, and I'm going to use that version 1.3.2 of the plugin, which is the latest version as of this recording, and I'm going to specify my Micronaut version, which is distinct from the actual plugin version as the latest version, which is 2.3.0. I'm also going to specify test runtime as JUnit. This allows the plugin to automatically configure JUnit 5 as my testing tool. And finally, I'm going to add an implementation dependency on Micronaut runtime, which is the only library, the minimal library needed for working with Micronaut at runtime. Finally, I'm going to set a class that's going to contain my main method for my application. In this case, it's going to be called example.application, which I haven't created yet, but I will do in a moment. Once we can say that, we can close that, and we can open it up inside VS Code. But before that, I'm going to create a couple of directories, one for my source Java sources and one for my test sources in source main Java and source test Java. We're now ready to open that up in VS Code. And here we have my Micronaut application ready to roll. So the first thing I'm going to do is I'm going to create that application.java file that I referenced in my build. In my example package, it's going to be an application class, and it's going to have a public static void main string array args method entry point, the typical entry point for Java applications. And within this, I'm going to call Micronaut.run and pass in the arguments to Micronaut in case it needs them. I'm going to import that class. And that's how you basically use Micronaut as an entry point in your application and set up DI. For testing, you can create a separate class for testing. And I'm going to create a application test.java file, again within the same package example. And I'm going to call it application test, if I can spell correctly. And I'm going to annotate it with Micronaut tests. What is Micronaut test? Micronaut test is the testing framework for Micronaut, and it lets you dependency inject beans and components into the test itself that you're running. So for example, I can use the @inject annotation from javax.inject to inject the application context. The application context in Micronaut is a bean container, which contains references to all the different beans that get created or are creatable. And I'm going to inject it, and I'm just going to write a simple test that asserts that I'm able to inject it into this test using assert not equals, I think. Probably the best for this scenario, assert not equals, not null, context. Okay, so that's it. So that's my test. So I can now effectively run this test, and lo and behold, the test passes as expected. So I'm able to inject my application context into my test class, and we're at the races. Now to run my my main method, I can do the same thing. I can run this main method from my IDE. You'll notice the output saying that Micronaut is starting up, although I get some SLF4J errors. This is because by default Micronaut uses SLF4J for logging. So you need at least one dependency in build or Gradle on an SLF4J provider like Logback or something. In my case, I'm going to use SLF4J simple, which is just a simple logging framework that will just write to standard out, which is fine for this demo. So once that's in place, we can run it again, and you'll see that this time I get some better logging output. But Micronaut just outputs that this is a CLI app and that no container was found, so it's running it as a CLI application. Now let's actually create something interesting. So I'm going to create a vehicle class inside my example package. And this is going to represent my domain role. So I've got a vehicle class. And a vehicle is going to have a engine that it's going to operate with. So I'm going to define engine as a constructor argument, a required constructor argument of the vehicle type. So I'm going to generate a constructor, and that's it. And if need be, we can also now notice that this class doesn't exist, so we need to create it. So I'm going to create that class, and it's going to generate the necessary class for me. I actually want this to be an interface, so I'm going to alter it to be a interface instead. And this is going to be my interface for starting the engine. So for the interface, I'm going to define a single start method. And then from the vehicle class, I'm going to define another start method that essentially starts the engine every time the vehicle is started. So we're going to call engine.start, and we're off the races. Okay, so that's it. So I've got my vehicle calling my engine to start, and that's it. So how would I make this component bean? So the first thing you need to do to make a class injectable by dependency injection is to add a bean scope. So I'm going to add the singleton scope. Now what is singleton? Singleton is from javax.inject, and it basically identifies a type that should only be instantiated exactly once. So a singleton type. And by adding it to this vehicle class, I've made this component available for dependency injection, and we're ready to go. So I'm going to try and inject this into my test. I'm going to inject the vehicle into my test, And then in my test, I'm going to try and call the start method that we defined earlier. So let's run this test and see what happens in this context. So I'm going to run the test. And we're probably going to have to show my console again. Focus console. Oh dear. Okay, so the test failed. That failed logically. It failed with a no such bean exception. Okay, that actually makes sense. As you remember, the vehicle requires an engine, and there isn't actually a engine bean. We only have an interface at this stage of time. So what we need to do is define a new engine implementation. So I'm going to define a V6 engine for my interface, and it's going to be in the same package once again. And it's going to be named V6 engine. It's going to implement engine. And then what I'm going to do is I'm going to generate an implementation for this engine of the start method. So I'm going to go to my source actions and generate implementation, and there we go. So we have my start method generated, and I'm going to provide an implementation that for the moment just outputs something useful to system.out, saying that this is the V6 engine, and we're going to start it, and boom, there we go. There's my V6 engine starting out. So now that's that done. Now the next thing to do is I should add a scope to this. So again, we can add the singleton scope. We could make it prototype, so a new engine is created for each car. But in this case, we're going to just use singleton. And now we can see that the test passes, which is great news. So that's the test. Now, what about the case where we want to actually run my application class and get this output? So by default, Micronaut is when you call the run method, it's just going to start up the Micronaut context. It's not actually going to invoke any beans within it. To do that, we need to make some modifications to my class to make that happen. So to invoke the engine and invoke the vehicle. So I'm going to actually make my application class itself a singleton, and I'm going to add to it a startup method that gets invoked when the application context starts. So we can listen for startup event. Now, startup event is an event that's fired by Micronaut when the context starts up. And we can inject my vehicle instance, if I can type, into my application class, and I can use source actions to generate a constructor for the vehicle again. And then what I can do is I can call vehicle.start from my startup event. Now, the only thing I have to do is make sure I annotate this with event listener to signify that the method is listening for startup events. So I add the event listener annotation, and now we should be ready to run my application. So if I run this now, you can see on startup it outputs V6, boom. So it's firing the startup event, we're listening, we're invoking the start method, and we're at the races. Okay, so that's pretty cool. We have some basic dependency injection working. Now, what if I wanted to drive, the whole point of dependency injection is to decouple implementation from the interface. So what if I wanted to drive a different implementation based on configuration? So what I'm going to do in this case is I'm going to create a new vehicle configuration, which is going to allow me to customize and provide different vehicle configurations based on the environment and configuration. So I'm going to create a class that is the vehicle configuration, and I'm going to annotate it with @configuration properties and vehicle. So there we go, there it is. And then I'm going to define an enum here called vehicle type. Or actually, no, let's call it engine type. That's probably more logical. And I'm going to support engine types of V6 and V8 in my configuration. And then I'm going to provide a property of this vehicle configuration that allows me to define the engine type via configuration. So there we go. We're going to define that property, and I'm going to generate a getter and a setter for it. And there we go. So we have a mutable configuration properties bean here that represents my configuration. And that's good. So now how would I dynamically, based on the configuration, create different implementations? So one way to do that, one possible way to do that is to no longer make this a bean. And instead of exposing this as a bean directly, I'm going to create a new engine factory class. And I'm going to put in the example package. I'm going to annotate it with @factory. And this is going to be my engine factory. And into the engine factory, I'm going to inject the vehicle configuration field type that I defined earlier. I'm going to make it a final field. Once again, we can generate a constructor for it. And that's it. We're at the races. We've got my configuration. And now what I need to do is define a method that produces a bean. So the way you do that is by finding the scope on the method itself. So I'm going to make the engine method return my engine implementation by annotating it with @singleton. And I'm going to pass in the engine type. So in the case of V6, I'm going to return my V6 engine. And otherwise, in the default case where we can't support that version, we're going to throw an exception. So we're going to throw a new configuration exception. And we're going to say that's an unsupported engine, or maybe we should actually provide a little bit more detail in the error message, unsupported engine type, and provide the actual engine type that's unsupported. Okay. So finally, if you also want to default to a particular engine type, we can make that into a particular engine type. In this case, V6 as the default value when none is specified. And we're ready to go. So with that, we should be ready to go. So let's go back to my main class and let's run my main method again. Open my debug console and run it again. And you see it's working. So it's basically defaulting to V6 because we don't have any configuration. Let's change that and actually create a main resources directory and create a new application.yaml file. Why did that come? Docker. And in here we can say vehicle engine type and set it to V8 instead of V6. And let's go back to my application class now and see what happens. So it actually failed, and it fails because we get that configuration description, unsupported engine type V8. V8 engines are not supported at this time by my factory, so that's exactly why specifying V8 resulted in an exception. So to solve that, I could come in here and create my V8 engine.java implementation and basically define a new class that represents my V8 engine. And again, once again, just implement the engine interface with something reasonable, generate an implementation for it, and this time essentially do the same thing: system.out.println, and output the V8 engine as my implementation. And maybe V8 engines make more noise, so we make a louder noise. Okay, so that looks okay. Now, just in my switch statement, we need to update that to handle the case where V8 is specified and return the new V8 engine. And we're at the races. Okay, so that's my factory implementation updated. Let's go to my main class and run that again. And as you can see, we have it working. So V8 is now configured and working. So we can change the configuration, alter the configuration, and switch between different engine types. And it's completely configurable via application.yaml and the injected vehicle configuration. Now, one thing I wanted to show you is that this is a class and it's mutable. So we got getters and setters. As you can see, for the engine type, we've got a setter, but we can also make it into immutable configuration. If we don't want my configuration to be modifiable, we can change this to be a interface instead, and get rid of that field and get rid of the implementation and get rid of the setter. And now we just have an interface that defines my configuration. And what Micronaut will do was that will at compilation time automatically implement this interface for you and provide an implementation that resolves the properties. So if we once again show my console and run this test, as you can see, we get the exact same behavior, exactly the same, just a lot more concise by using a vehicle configuration interface with simple getters on that get implemented for you at compilation time. In Micronaut 2.3, you can also use records as well, which is pretty cool for configuration properties. Okay, so so with that done, I'm going to actually clean up here since it's no longer being used. I'm going to disable I'm going to show you a different technique for doing this. I'm going to disable my engine factory, and instead I'm going to replace it with @named bean. So I'm going to use javax.named and add @named v6 to this engine. And I'm going to go to the other one, I'm going to add @named v8. So remember, I've disabled my engine factory, so that's not working anymore. And instead of my injection point, I'm going to inject a named bean here. And what I'm going to do is I'm going to use a property expression. Oops, they've got to be surrounded by $ in curly brackets. So I'm going to say vehicle.engine.engine type. And I'm going to use a colon, which allows me to specify a default value of v6. So if it's present, it'll get injected. If it's not, it'll use v6. And that allows me to dynamically configure the name of the engine that gets injected without even involving the factory. So let's run that and see what happens. As you can see, we get v8 room. And if we come to my configuration, we alter that to v6 and we run it again. You got v6. So as you can see, without even involving complex factories, you can just use dynamic property expressions to alter how things work. So let's clean up and get rid of that factory since we're not using it anymore, and look at a different technique for doing this. So sometimes you want to use different engines based on the environment, for example, locally or in the cloud. So what I'm going to do is, instead of using @name, I'm going to make this singleton. And I'm going to say that the V8 engine requires, using the requires annotation, the environment to be environment.oracle cloud. So the V8 engine, we have more processing power in Oracle Cloud, is going to use the V8 engine. And locally, singleton, I'm going to say requires, and I'm going to say not environment Oracle Cloud. So when we're not in the Oracle Cloud environment, use the v6 engine, and when we're in the Oracle Cloud environment, use the other one. We can just remove this property expression. And now let's see what happens when we run my application. So I'm going to run it. And what happens is we get the v6 engine because we're running locally. We're not currently running on Oracle Cloud. So how do we simulate running on Oracle Cloud? So if I just change this to build args, and then I use the environments method to tell Micronaut that we're actually, really in Oracle Cloud, and we click start. Now, when I run this application again, you will see that V8 engine is output. So as you can see, when you're in Oracle Cloud, it's using V8. Now, you don't normally have to be explicitly specify environments here. What Micronaut will do, Micronaut will automatically detect the environment that you're in. In fact, there is a way to do that called deduce environments. You can disable it if you want, or the default is set to true. And what Micronaut will do is it will automatically detect when you run in Oracle Cloud or Amazon Cloud or whatever cloud, and it will automatically detect the environment and allow you to adapt your application based on whether you're running in the cloud or not, which I think is pretty cool. So now I'm going to show you a different way to do this. So instead of using environments, what I'm going to do is I'm going to do, say, @requires property equals, and the name of that property that we have in application.yaml. So if you remember, it's vehicle.engine type. So I'm going to say @requires property vehicle.engine type value equals v8. So this one will be active when it's set to v8, and the other one will be active when it's set to v6. There we go. So that means we can configure different beans based on configuration just using bean requirements, which is another alternative approach to doing this. So let's run that application again and see what happens. So when I run this application, as you can see, we get the v6 output because it's set to v6 in the configuration, but we can alter that to v8 and run it again. And there we go, we get the v8 engine in operation. Okay, so what's really powerful about this though is when you start mixing in cloud-specific configurations. So I can create an application.oraclecloud.yaml or aws.yaml or gcp.yaml, and I can copy that in there. So I can say I'm going to use v8 on Oracle Cloud and I'm going to use v6 by default. And then when I run my application now, you'll see the output is v6, which is expected because that's the default. But then I can go back and alter my startup process again. Oops, if I can type correctly with the build method, no. Okay, environments, there we go, environment.oracle cloud and start. And now we effectively get the same results, right? So Oracle Cloud is environment and v8 room. By activating the Oracle Cloud environment, Micronaut will automatically detect the Micronaut application Oracle Cloud.yaml, load it, and apply that different configuration based on the cloud that you're running in, which I think is pretty neat. So that's another way to do it. Now I'm going to look at how you can apply some AOP advice. So we got this engine interface, got the start method, and I want to apply some advice to it. So I'm going to add a track start.java annotation inside the example package, and it's going to be track start. I'm going to call it track start. It's an annotation, and I'm going to add the around advice annotation. And the around advice annotation basically says I'm going to decorate a method invocation such that a method can be intercepted by a method interceptor. So I'm going to need a method interceptor. So I'm going to create a new track start interceptor.java file, and again in the example package, and I'm going to name it the right thing, and it's going to implement method interceptor, passing a couple of just generic object arguments, and I'm going to generate a implementation of the only method you need to implement, which is intercept, and I'm going to make this a singleton interceptor. And for the moment, I'm just going to proceed with invocation and return the result, and just output to system.out the name of the method that's being intercepted. So let's output that, get method name, there we go. And that's it. Now the only thing that we have to do is make sure my annotation is retention runtime, since we don't want to be source retention, and apply the intercepted type, which is a context annotation.type, that we want to apply every time this annotation is used. So I'm going to add the track start interceptor, and then we're going to go to my engine interface and add this annotation to the interface. Now the powerful thing about adding it to the interface is every time somebody implements this interface, they will automatically get this AOP advice and additional behavior applied to their new implementation of the engine interface. I'm not applying it to the implementation, I'm applying it to the interface. And so let's see what happens when we run this main method. And as you can see, we get the method start output, which is amazing. So every vehicle implementation that implements the engine interface is getting AOP advice applied, which is really, really cool. Now let's make this advice do further decoupling. So currently the implementation of this device is just outputting the method name. But let's get it to actually trigger an event. And a good way to decouple application architecture is through an event system. So what I'm going to do is I'm going to add the ability to publish an event. I'm going to create a new event here called engine start event.java. And this is going to go into the example package. And once again, every time an engine is started, we're going to trigger this event, which allows me to publish information about the engine starting, which other event listeners can listen for, and extend my application without introducing coupling, which is really, really critical. So I'm going to add engine event that takes in the engine. And inside my interceptor here, I'm going to publish the event. So what I'm going to do is I'm going to get the target of this event, which is going to be the engine, like so. And then I'm going to inject into my interceptor the application event publisher, which is the event publisher. And I'm going to add a constructor argument for this, this event publisher, so it gets injected. And then I'm going to call event publisher.publish event and publish a new event engine start event. So now every time somebody starts an engine that of an implementation, this event will be triggered by the application, which I can listen for anywhere or anywhere I want to. So I can add an event listener here, or one or many different event listeners, to listen for engine start events and act on them as they happen. You could, for example, log them or publish them to backend systems or metrics or anything like that. And for the moment, I'm just going to print it out. I'm going to print out this, that the engine is starting, and just output the event, the engine. We can't get the engine type. No, we'll just have to output the engine for the moment. I'm still got to what's wrong here? Missing semicolons. I always forget when I'm in Java, so we have to add that semicolon. And there we go. There's my engine start event listener. And now when we run my application, you'll see that what happens is the event gets published, and look, we get the engine started event triggered. So we have this nice decoupled architecture between the implementation publishing the event. Every time the start method is called, when somebody comes along and adds a new engine, this behavior is automatically applied. And we can even add things like async. So I can add an async annotation to the event listener and listen for events asynchronously so they don't block the implementation of the start method. And so if we look at the output again, you can see that the engine started output actually appears after the broom message. And that is the demo. So in summary, Micronaut provides awesome build time dependency injection in AOP. It's fully compatible with GraalVM native image out of the box because it's not using any reflection, any runtime proxies, anything that would interfere with the closed wall static analysis. And it's flexible enough to be used in a range of scenarios beyond just microservices. As you saw, I used it for CLI applications in this demo. Some resources: come speak to us on Gitter, the user guide for more documentation, create your applications today on Micronaut launch at launch.micronaut.io. Check out the guides at guides.micronaut.io, and follow us on Twitter and star us on GitHub. Thank you very much, and it's time for a Q&A session, and I hope you enjoyed this session.